Section 4.5, exponential and logarithmic equations and applications. We'll now have exponentials with the equal sign or logs with an equal sign. Easy enough. The first way we're going to solve exponential equations is to get the same base. Do these sides of the equation have the same base? Is 8 the same as 16? No, so the base is not the same, but could I make it the same? 8 would be what? 2 to what power? 2 cubed, that's right. And then we still have the x plus 2 in the exponent position is equal to, and 16 we could write as what? 2 to what power? 2 to the 4th is right. So what's our rule of exponents? So a power raised to power. Do I add or multiply? Multiply. Okay. So I have 2 to the power of 3 times x plus 2 is equal to 2 to the power of 4x. Any ideas what we can do if the base is the same? Cancel what? The base? Yeah, that's true. That is true. We cancel a base, but we need to do something to cancel. We need to do the inverse of 2 to the power. No. Okay, the inverse of x squared is square root. The inverse of 2 to the x is what? I should have put this on the test. Yeah, log of 2, right? Log base 2? Yes. So that's how we get to cancel. We do log base 2 of both sides. 3x plus 6, 2 to the power of 4x, and those undo each other, and we're left with only the exponent. 3x plus 6 is equal to 4x. Now, most people just skip to this step, and I'm okay with you doing it. But understand, we're doing the inverse operation. We're undoing the 2 to the power. And then we subtract 3x from both sides. 6 is equal to 4x, so x is equal to... No, wait, what happened? 6 is equal to x, and we're done. Any questions about that? Do I have to check my answer? I can, I don't have to. So if I plug it in and it gives me a wrong statement, like 0 equals 6, what does that mean? It means I did something wrong, right? So this is an example of a problem I do not have to check. Use logarithms. Okay, so this first method was get the same base, always or doesn't always work. The second one is to use logarithms. I can't get the same base, right? I don't know what common base there would be between 2.7 and 3, but I want to get rid of the exponent. And how do I get rid of exponents? You take the log of both sides. What's your favorite logarithm? Log base 10? Great. So I'll take log base 10 of both sides. 2.7 to the power of x of 3. And the exponent rule brings this exponent out in front. So we have x times log base 10 of 2.7. So I don't have to write the 10 because it's a common logarithm. And then how do I get x by itself? Yes, divide. This log of 2.7 is just a number. So we divide that number. X is equal to log of 3 over log of 2.7. You can leave an exact form on the test. This is approximately 1.1061. Maybe practice entering these in your calculator. The next one's more difficult. I look at 2 to the power of something and 20 and ask myself, can I get the same base? If I can't, I'll take the log of both sides. Can anyone guess my favorite logarithm? The natural logarithm. Why would that be my favorite? Because it's less letters to write. Natural log of 2 to the power of 4x minus 2 of 20. We can now take the exponent down in front and multiply by it. 4x minus 2. And just make sure you put in parentheses because we're multiplying the entire exponent times the natural log of 2 is equal to the natural log of 20. We want to get x by itself. What should we do? Divide by natural log of 2. 4x minus 2 is equal to natural log of 20 over natural log of 2. We'll add 2 to both sides. Natural log of 20 over natural log of 2. And divide by 4. Multiply by 1/4. Which do you prefer? Times 1/4? I do too. Because it's easier to think of this as distributing, I think. Especially when you have a fraction here, natural log of 20 over natural log of 2. Just think of it as distributing a 1/4. So we get x is equal to 1/2 plus natural log of 20 over 4 natural log of 2. I'll certainly accept this as your final answer in exact form. Math people like exact form, which is approximately 1.5. So you should think to yourself, if I have a variable in exponent position, I'm going to take the natural log or some logarithm on both sides to bring the exponent down. We're going to skip this. I took this type of problem off your homework. It's quadratic in form if you want to practice that. Just for fun, won't be on a test. Now we're going to solve. We'll either have some logarithm equal to a number or a logarithm equals to a logarithm. And we'll just do the inverse operation. Let's maybe do a very simple one quickly. Log base 3 of x is equal to, thank you, 27. How do I get x by itself? What's the inverse of log base 3? 3 to the power of both sides. Log base 3 of x of 27. Maybe I picked too large a number. So what happens when I take 3 to the power of log base 3? They cancel and I get x by itself. Yeah, that's a huge number. Would the calculator even handle this? I'm curious. How many digits do I have? 3 to the power of, yeah, there's no way, right? Hey. Okay, Microsoft calculator. Probably not your calculator though, right? Yours got it? Wow. Nice. Okay, the most important thing here is while the exponentials, it was optional to check our solutions for logarithmic equations, it's not optional. You may create extraneous solutions, things that look like solutions that aren't. And it has to do with the domain. What's the domain of a logarithm? That's the range. The inside, yeah, 0 to infinity. The inside of a log, we must check the inside of the log is positive. That means not 0, not negative. Let's try the first example. What's the inverse of log base 2? 2 to the power. What's 2 to the power of log base 2 of 2x minus 3? So these undo each other completely because they're inverses, and we're left with only the inside. 2x minus 3 is equal to, what's 2 cubed? 2 times 2 is 4. 4 times 2 is 8. So we add 3 to both sides. 2x is equal to 11. So x is equal to 11 halves. Now we must check every time we start with a log equation. And when I say check the domain of every log expression. So what I mean by that is I look at log base 2 of 2x minus 3, and we plug in 11 halves. All I care about is to simplify the inside. I want to make sure it's positive. I would get 11 minus 3 is 8. Positive, therefore, this is not an extraneous solution. Any questions about that? All right, next problem. We want to solve this, find all values of x and make this true. What should I do first? Inverse? What's the inverse of log? 10 to the power, right? So the question is, should I do the inverse operation first or simplify first? Simplify is easier. You could technically do the inverse, but I find people usually mess up. We'll make this note. Combine all logs first. So how do I combine these? Log base 10 of x minus 2 over x. Does this look familiar? Okay, is equal to 3. Bless you. What's the next step? Inverse of log base 10 is 10 to the power of both sides. So these undo each other on the left-hand side, and we're left with x minus 2 over x is equal to 10 cubed is 1,000. We're left with the rational equation. How do we solve it? Multiply by x. X minus 2 is equal to 1,000x. Yeah, because the x is on the same side. Negative 2 is equal to 999x. So x equals negative 2 over 999. So we must check. Take the first logarithm, log of, we'll plug in negative 2 over 999 minus 2. And I don't really need to simplify it. I know that is negative. So that's a domain error, which means this is an extraneous solution. Any questions about that? Do you believe me? Negative 2, if we take the log of it, invalid input. It's nonsense. It's not in the domain. The next problem. What should we do first? Does it help you when I show you common mistakes, or does it just confuse you? Okay, if it doesn't help you, don't look. So the most common mistake is people do the inverse operation like this. Looks good. What's the problem? You have to do 4 to the power of each side completely. You'd have to do 4 to the power of this side completely, which is your rule of exponents says that the one left simplifies to if we have an exponent there, let's say x to the power of a plus b is equal to x to the power of a times x to the power of b. So this plus becomes a times. Log base 4 of x times 4 log base 4 of x minus 2. So it ends up being x times x minus 2, not a plus. Times, not addition. Okay, so I'm just pointing that out as a common error. But let's do this the way that's recommended, which is to combine logarithms. So what's the rule? How do we combine these? X times x minus 2 is equal to log base 4 of 15. Once we have a single log on each side, we can do the inverse, and the inverse is 4 to the power of the side. 4 to the power of log base 4 of, I'm going to simplify this as x squared minus is equal to 4 to the power of log base 4 of 15. We get just the exponents equal because these undo each other. We get x squared minus 2x is equal to 15. Any questions about that? And you all know how to solve quadratic equations. Subtract, make one side equal 0, and use your favorite method. Hopefully factoring works. X minus 5, x plus 3. So our work leads to solutions x equals 5 and x equals negative 3. Do you think they both work? Which one do you think doesn't work? Do we always cross out negative numbers? It's tricky. We haven't encountered one where we haven't. But no, negative numbers can be solutions. I'll give you one example here. If I had log of 5 minus x, then I'm saying whatever's in here I would want a negative x to cancel to make it positive inside the logarithm. 5 minus x must be greater than 0, which means x is less than 5. So an example like negative 10 is fine. If I got an answer like negative 10. I can't take log of a negative number, but the negatives would cancel and I get a positive number. Negative 10 is in the domain. This next one, what should we do first? Yes, combine. So I get log base 5 of what? 3x over x squared minus 1 is equal to log base 5 of 2. Now, you do enough of these, and I'm okay with you skipping straight to 3x over x squared minus 1 is equal to 2. I'm doing the inverse of each side because it's the same log on each side. Now we solve the rational equation. So we multiply both sides by x squared minus 1. Then we're left with a quadratic. And we solve the quadratic by making one side 0. 2x squared minus 3x minus 2. These are usually factor. Factors of negative 2 are negative 2 and positive 1. So guess and check. This multiplies to make x. Minus 4x is negative 3x. So what are my solutions? X equals negative 1/2. X minus 2 equals 0, or x equals 2. So when I check, I always plug back into the original. Log base 5 of 3x. And I can't take log of a negative number, so I'm going to have to toss it. We can look at the next one. Log base 5 of 3 times 2. Sure, that's positive. That's okay. Minus log base 5 of 2 squared minus 1. That's positive. That's okay. It must check out in the domain of all logarithms. If it fails one, then it's invalid for the whole equation. Any questions about this? Okay, now we're to the application problems. For the log one, I'm going to refer you to the one we did last week. Let's see. Yes, the earthquake one. 4.4, last question. So let me just state a few things here. We make a logarithmic equation when we want to make things much smaller that are very large, or if the difference between them is very large. Because 10 to the power of x, if I plug in a number, it makes it much larger. So the opposite of that, log base 10 of x, if I plug in a number, it makes it much smaller, the inverse. Does that make sense? When there's a large variation of things, like sound, I could whisper to you, that'll have a certain decibel level, or I could play the sound of a jet in this room, and then we could all go deaf, right? Those are so different that to tell the difference, we take the log. Because, for instance, what is log of 1,000,000? Anyone tell me? Log base 10 of 1,000,000. Yes, it is 6. 10 to the 6th, the answer is 6. And what is log of 1/10? It's 10 to the power of negative 1. So the answer is negative 1. So I can much more easily compare these numbers, 6 and negative 1, than 1,000,000 and 1/10. This is why we use logarithmic equations, to make things smaller and easier to compare. The other thing is it maintains the order. 1,000,000 is much larger than 1/10, but when I take the logarithms, it maintains the order. 6 is larger than negative 1. Okay, but I want to talk about the compound interest problems that you'll encounter. A stands for annuity. P stands for principal. R is for interest rate. T is for time. N is for Number of times something's compounded per year. Number of times. We're usually talking about money. Money is compounded per year. So perhaps I should make a table really quickly. Let's say I have a time scale in years. Let's say I make 10% on my money per year. Let's say I start with $100. After 1 year, how much money do I have? I made 10%, right? So 100 plus 10% of that. Okay. Now, simple interest would be like saying annual simple interest would tell me that I'm just going to make $10 each year, okay? Because it's a simple calculation. But what is a more difficult calculation is, what if I make interest on my interest? Compounded, we call that compounded interest. The first year I make 10%, I have $110. The next year I make $10 on the 100, but then I make 10% on my interest. What's 10% of 10? So I make an extra dollar because I earn interest on the interest. Do you understand this idea of compounding? So the next year I would make $10 on the 100. I'd make an extra $1 on the 10. And I make an extra what on the 1? I'd make an extra 10 cents. So over time, it starts adding up like significantly. That's what's called compound interest. Your interest earns interest. This is the formula for compound interest. Okay, so let's talk about how to analyze this. I have 12,500 invested at an annual interest rate of 8%. This would be my principal, money invested. My interest rate would be R is equal to 0.08. And this is number of years. T is equal to 10 years. In the first case, if my money is compounded annually, N is equal to 1, it's compounded once a year. My formula, A is equal to P times 1 plus R over N to the power of NT. I'm going to plug in 12,500 times 1 plus, I'll plug in 0.08 over, and we're saying N is 1. 1 times the number of years. We plug that in our calculators, and we get 26,986 and 56 cents. Not bad, over doubled our money. By the way, if you're buying a house right now, interest rates are about 8%. In a car, more like maybe 9 or 10. Over 10 years at 8%, you're paying over double the price of the house. Kind of crazy. Okay, what if the money is compounded daily? How does that change my equation? Now my N changes here. My N will be what in this case? How many days are there in a year? 365. So my equation is 12,500 times 1 plus 0.08 divided by 365. So this is making this number smaller, right? But then it's making the exponent larger. Which one do you think wins? The exponent. It's compounded more times per year. So in the first equation, we just took the interest at the very end of the year and did it again at the end of the second year. This one, every day we're saying how much interest. The next day, let's earn interest on the interest. So you think this will be more or less money than 26,000? More? How much more are we guessing? 27,816.82. Is it worth it? Yeah, you just change a little number and you get more money. Why not? Okay, what if we compound the money hourly? What does that mean? We earn interest on our interest every hour instead of every day. So what is n in this case? How'd you get that? 24 hours a day times number of days equals, that's right, 8,760 hours in a year. Do you ever know that? I didn't remember. 12,500 times 1 plus 0.08 over 8,760 to the power of 8,760 times 10 years. Do you think we make more or less money? More? How much more are you guessing? $27,819.16. Over 10 years, we made an extra what? Not even $3. But it's for free. Because I'm just changing the number of times it's compounded. Okay. Bankers, if they give you a loan, how often do you think they'd compound the money? They want to make as much money as possible, so compound hourly. Could they do secondly? Could they do? I'll tell you what they do. They send n to infinity. They literally send n to infinity. So it's called compounded continuously. And what happens as you have this number go to infinity is this magical number e occurs. And so the equation changes to p times e to the power of rt. If you see it continuous compounding, we're going to use this equation instead. If you want to prove this from scratch, we'd like to take first quarter calculus. Find the balance if 32,000 is invested at annual rates of 8% for 3 years, compounded continuously. So compounded continuously tells me A is equal to PERT, P times E to the power of R times T. What's my P value? Yes. That sounded like statistics. 32,000 times e to the power of, what's my rate? 0.08. My time is 3 years. So practice plugging that in your calculator. 32,000 times, do I have an e button? Yeah. E raised to the power of 0.08 times 3. Is that right? It is right. I really don't like this calculator. The order I have to plug things in is really awful. 40,679.97. When I wrote these notes 10 years ago, 8% would sound like a lot of interest. Now it's like standard. How long will it take $1,000 to triple if it's invested at annual interest rate of 5.5% compounded continuously? So compounded continuously tells me we're using that same formula. A is equal to, yes, PERT. So what can I plug in? Yes, principal is 1,000. Very good. What else? E? Yeah, E is just a number. Bless you. The rate? Sure. 0.055. Then what? How long will it take? Tail, take. T is the unknown, right? Leave it as T. It's a variable. What about A? I can't have two unknowns. Close to 3. Triple. So triple what? 3 times 1,000. Yes, 3,000. This is more tricky because we're plugging in an A value. It's not explicitly stated. It can be even more tricky, and it can, sometimes they won't even tell you how much is invested. It is possible they would just write P times E to the power of 0.08 0.055 t is equal to, and triple would be 3p. These are done the same way. It's also more difficult because we need to solve for an exponential. How do we solve? Oh, I always forget this other zero. I first want to get the exponential by itself. So let's divide both sides by 1,000. We get 3 is equal to e to the 0.055 t. So why are these problems the same? Because here I would just divide both sides by p, and I get 3 is equal to e to the 0.055 t. So this problem actually gave you more information than you needed. You don't need to know the actual principle. You can still solve it. You'll get the same equation. Think back to 40 minutes ago. How do we solve this type of equation? Yes. Which log do you want to use? Yes, inverse of e is natural log. Take the natural log of both sides. E to the power of 0.055 t is equal to natural log of 3. And these are inverse functions, so the answer is just the exponent. 0.055 t is equal to natural log of 3. And we'll divide both sides by 0.055. T is approximately equal to 19.97, or about 20 years to triple our money. Are there any questions about this? We do have more time, so I'm going to go back to that problem I skipped. Suppose that the sound at a concert measures 124 decibels. Use this formula where the intensity of sound is I. Variable represents the loudness of sound. Let me move this to the side. Okay, so let's do part A. Is it telling me what the loudness is? Oh, sorry, this is the decibel, right? So that is the loudness. So we'll plug it in and we'll say 124 is equal to 10 log of I over I naught. Any questions about this? Okay, so we're solving a logarithmic equation. How do we solve? First, get the log by itself. So we'll divide by 10. 12.4 is equal to log of I over, what's the next step? We want to do the inverse of log base 10, which is 10 to the power of both sides. 10 to the power of 12.4, it's quite a large number. 10 to the power of log of I over I naught. And on the right-hand side, they cancel. I over I naught is equal to, what did you get in the calculator? 10 to the 10 raised to the power of 12.4. That's quite awful. I'm going to leave it. I'm going to leave it as 10 to the power of 12.4. So I is equal to 10 to the power of 12.4 I naught, which we can multiply by this definition of I naught, which is 10 to the power of negative 12 W over M squared. So we can add these exponents. If they add together, what do we get? 10 to the power of 0.4 W over M squared is going to be our intensity. If the threshold at which sound becomes painful is 1 unit of W over M squared, will the music at this concert be physically painful? Is this greater than 1 or less than 1? Greater than 1. So yes, it will be painful. 2 point something. Painful. Take earplugs. This is